Today we're going to look at entropy. When we talked about energy, I said that it was a very vague concept because basically everything was energy. Entropy is highly entangled with energy, and it's also vague because basically everything is entropy. The definition that the IB would like you to have for entropy is that entropy is a measure of the degree of disorder. So there's your key word, disorder, in a system. So perhaps two of the questions that you have right now would be, is it easy to recognize disorder in a system? And secondly, is it possible to quantify? Can we measure disorder? So the first question is, can we recognize situations where there's more or less order, more or less entropy? What I'd like you to do is pause the video and identify in each one of these pairs which one you think has more entropy, more disorder. Then come back for the answer and explanation. So you probably chose this one, and this one. And something you want to notice about those three choices is that they're all warmer. And we can kind of make a general rule that where things are warmer, that means more entropy. These could be molecules in a solid. These are the same molecules in a gas. But you can see there's a lot more order in the solid. Same thing here. Crystal lattice structure for the ice. A lot more ordered than the blob of water. And then the warm molecules, they're jiggling around a little bit more. They have a little bit more kinetic energy. So there's more disorder in a room full of dancing people than a room full of sitting people. So we want to make a general association between things being warmer and there being more entropy. Same game again. Pause the video, make your predictions, come back for the answers and explanations. So you probably chose this one, and this one as the three cases with a higher entropy with more disorder. And the common theme to these three is separation. When we separate things, there's less entropy. Or conversely, we could say when we mix things, there's more entropy. So when we do things like separating hot from cold, separating positive charge from negative charge, separating mass, then in all those cases, you're lowering the entropy, and that makes energy available. And some more pairs. Pause the video, make your choices, come back for the answers and explanations. Okay, for more entropy, it's the pile of sand, and it's the mixed up letters. And the common theme here is probably information. You've got a lot of information about castles here, which you don't have in the pile of sands. You've got information about entropy in this sentence that you don't have in the mixed up letters. So carrying information requires low entropy. Where lots of information is represented, you must have low entropy. And you can't represent things with randomness. What I'd like you to do in this exercise is identify in each pair which one would have to occur first in time. Pause the video, try that now. Now, it's very unlikely that these molecules moving around randomly would somehow organize themselves in a corner. It's much more likely that they're going to start out in a corner and then through their movement arrange themselves randomly. And the same thing here. The water isn't going to freeze into a cube, but the cube can melt into a puddle of water. And you'll notice in both cases, we're going from low entropy on the left to high entropy on the right as time advances. That is to say that there's a tendency for systems to move towards higher entropy. And later on we're going to qualify this a bit and make it into a law. Now we're going to watch a little music video by the filmmaker Messe Kopp. I think it's going to teach us a lot about entropy, time zero, and reversible processes. So here's our guy walking along Whoa, must have a magnet in his hand, picked up those glasses, scratching his head. What's that guy doing? The people are walking backwards. Wig. Another magnet, I guess. Another magnet. Wow, that was clever. Now he's sucking all the cards up into his hand somehow. Interesting tricks with magnets. People still walking. Oh, guy's riding his bicycle backwards even. Sucking some more stuff up into his hand with magnets, and then he's just putting them together. Hey, he's putting together a flower. He's giving the girl a flower. What a nice guy. And now what's he doing? He's taking it. He's putting together a table. That's a table he's putting together. What a nice guy. He's giving it to the couple there and arranging their table. Now look at the mess. He's cleaning up all that water off the floor. He's cleaning that all up. Oh, and then he puts a cap back on it and he's going to give it to this girl here. What a great guy. Okay, you've probably figured out what's going on. He's really walking backwards and the video's being played in the opposite direction. Let's watch it in the correct order. So he takes this bottle, he shakes it up. Now he's creating a mess. He's getting the water all over the street. What a jerk. He's wrecking their table. And now he's breaking the table all apart. And everybody's running away from him. He's kind of scaring them. Grabs this flower from the girl. And now he's just making a mess, tearing them all up and throwing them all on the floor. And now he's got his cards. He's littering. He's littering his cards all over the street. Throwing away his hat. He's got a wig on. He's throwing away his wig. Throwing away his sunglasses. There's a very important lesson that I want you to get out of that video, though. Some of the things in the video looked just plain wrong. And I'm referring to when he, say, reassembled the flower. Or when he reassembled the table, including the chess pieces on it. And when you think about those processes, they involve a very large increase in entropy. A flower has a lot of order. When you tear it up, you've got a very large increase in entropy. You've got a nice organized table set up with chess pieces. You throw that all over the place. That's a big increase in entropy. So these involved a large increase in entropy. But some things in the video looked pretty normal. In fact, much of the video looked quite normal. Walking backwards looked just like walking forwards when it was shown in reverse. Now, if he had had muddy shoes on and he was leaving a mess behind him, if he was causing an increase in entropy, then it would be quite noticeable when the film is reversed. And so if you think about these things that looked quite normal, they involve a very small or negligible increase in entropy. And that leads to a theoretical idea, and that is a process where there's no increase in entropy, and we'd say that that process was reversible. If we were to show it on film, it would look perfectly normal with the film going in either direction. If delta S, the increase in entropy, is equal to 0, then the process is what we call reversible. And that idea of a reversible process is very, very important in thermodynamics, and we'll talk more about it later. This really interesting video shows 3 colored blobs of corn syrup, and they're rotated in some sort of a gel. This fabulous video was made by the University of New Mexico Physics and Astronomy Department. So he rotates it. It looks like everything's getting all mixed up. There seems to be a big increase in entropy. And now he reverses the rotation. If we think about putting milk in coffee and stirring it, there's no way you can reverse the direction of your stirring and get the milk back as milk itself. But watch what happens here. The blobs are starting to reform. It's as if the language of the blobs gets translated into some sort of code, and then by reversing the direction, the code gets translated back into the globs. And this would be what we consider a reversible process. It looked like there was a big increase in entropy, but there really wasn't. We noticed that we could tell that time was going backwards when entropy was decreasing. So for instance, when the flour was reassembled, entropy decreased, and we knew that couldn't be true. So we can say that normally, as time advances, entropy increases. Now, you might come up with a counterexample to that, and you might say, but what if I've got a big pile of sand, and I take a video, and some people form it into a castle? Then clearly entropy is decreasing. Now, if you rolled this one backwards, it's not hard to take a sandcastle and turn it back into a pile of sand. It's hard to go in the opposite direction. So when we think about the entropy increasing, we have to consider the whole system. So it wouldn't just be the sand, it would also be the human being here that's forming the sand into a sandcastle. And of course, all kinds of energy has to be flowing through this human being. And where is this energy coming from? Well, the human being goes through this process where it takes beautiful items like apples and bananas and turns them into rather crude stuff. In other words, there's a big entropy increase associated with that energy the human being is using. So it's not true that entropy always increases, unless you're talking about a closed system. So the entropy of the sand, it's decreasing. But the closed system of the sand plus the human being plus the environment, that entropy would have to increase as the sandcastle is built. So we say that the entropy of a closed system always increases. And perhaps the only closed system is the universe, but nowadays we're talking about multi-universe theories, so even that kind of falls through. There were also some processes that looked reasonable in forward or in reverse, and we call those reversible processes. And some key examples from the videos would include walking, or that demonstration where the droplets of corn syrup reformed. And in the reversible processes that we witnessed, there was a very negligible increase in entropy. Walking has a very small increase in entropy, unless you've got dirty feet. So in a perfectly reversible process, we say that the increase in entropy is zero. There is no increase in entropy. Well, earlier we talked about the first law of thermodynamics. So you're certainly expecting there to be a second law of thermodynamics. And it's that statement that I just made. Symbolically, we'd write that the change in entropy of a closed system has to be positive. That is, that entropy always increases. Now that's just one statement of the law of thermodynamics. It's probably the most fundamental of the statements, but there's other statements. There's a Clausius statement and a Kelvin statement and a Kelvin-Planck statement, etc. And we're going to talk more about those. But for right now, this is our statement of the second law of thermodynamics. Now here's a case where it seems like the second law is being violated. Take the case of a lake. If the air gets cold enough, of course, the water freezes. And we know that ice has lower entropy than water. So that ice is going to have lower entropy. So it would seem on the surface that the entropy is decreasing and not increasing in a natural process. But we have to keep in mind that word closed, because the ice is not a closed system. And you'll recall, when ice melts, it absorbs energy. And when ice freezes, of course, it's going to release energy. So during that freezing process, energy is released. Heat energy is released. And that means that the surrounding environment is going to be warmer than it would have been if the water had not frozen. And that means the entropy of the environment is going to increase. So we'd have a delta S for the environment that's going to be positive. And we're going to have a delta S for the ice, which is negative. And the magnitude of that increase is going to be bigger than the magnitude of that decrease. And so in the end, delta S for the system, environment plus ice, is going to be greater than 0. Here's another example where it certainly seems as if the second law is being violated. So let's put oil and water into a test tube. Then originally it's going to be all mixed up, so you're going to have a mixture. But if you wait a little bit of time, then the oil and the water will separate. The oil will go to the top and the water will go to the bottom because it's more dense. So our entropy of the mixture is definitely bigger than the entropy of the oil plus water. So that would mean that our change in entropy is less than 0, and that would violate the second law. But once again, we've got to consider the whole system. So pause the video, have a go at this, see if you can figure out why the second law is not violated in this situation. So we have to consider the fact that our sample is not a closed system because it's interacting gravitationally with the Earth. And that interaction, you'll recall, it's that gravitational force between the center of mass of the Earth and the center of mass of the mixture. And something's happening to our center of mass because originally that center of mass is going to be right here in the center of the mixture. But because the water is more dense, that center of mass is going to lower slightly. So we'll get a lowering of the center of mass. So if we consider the distance from the center of the Earth up to the original center of mass, let's call that the distance to our mixture of oil and water. And we consider this distance from the center of the Earth up to the center of mass when the oil and the water are separated. We'll call that ds for when they're separated. Then of course dm is bigger than ds. So that would mean our masses are more separated originally. The distance from the center of the mass of the Earth to our mixture is longer than the center of mass from the Earth to when the oil and water are separated. And that means we're going towards less separation, and that means more entropy. So we get a delta S here that is going to be greater than 0. Let's call this first delta S1 that was negative, and we'll call this second delta S2 that's positive. Then so long as delta S2 is bigger in magnitude than delta S1, that would mean that delta S for our system is going to be greater than 0, and the second law is not going to be violated. An interesting theoretical idea that comes from the second law of thermodynamics is called the heat death of the universe. So right now in our universe, we have all kinds of different things at all kinds of different temperatures. We've got some things that are cold, some things that are hot. And of course, heat's going to flow from hot to cold. And when that happens, you get warm mixtures. Things start to become more and more similar in temperature. And if we carry out that process indefinitely, eventually everything reaches the same temperature. Once everything reaches the same temperature, you can't have any more heat flow. And if you don't have heat flow, you can't use heat to get work. Let me write that down. When everything is at the same T, heat cannot flow. And if heat can't flow, that implies that heat can't do work. So we might have all this kinetic energy in the molecules, but we couldn't use it to do work because we couldn't get heat flow from one temperature to another. And naturally, we refer to that as the heat death of the universe. Okay, I have a little scenario for you. We've got a very messy child named Quebert, and there's two identical rooms in his home. In one of them, his mother has just tidied up, so it is looking spick and span. Everything is exactly in its place. And in the other room, identical room, but it hasn't been cleaned for a while, so it's already a little bit messy. Let's suppose Quebert goes into both rooms. Which room is his mother likely to be more angry about when he goes into the room and does his usual messing up? And I'm sure you said it was the room that his mother had already tidied up. Now, as it turns out, the way that Quebert messes up a room and aggravates his mother is very similar to the way that we calculate entropy changes for simple substances. The IB gives you this equation here. So if we add heat to a substance, then of course the molecules jiggle around more, and that causes an increase in entropy. So this is the heat added, and that's like the very energetic Quebert coming into the room and moving things around, shaking things up. Now, if a substance is at a low temperature, it's very ordered. If it's at a high temperature, it's not so ordered. So the temperature on the bottom there is kind of like how tidy the room is already. If it's at a low temperature, it's very tidy. If it's at a high temperature, it's not so tidy. And if it's at a low temperature, you're going to get a big increase in entropy. If the substance was already at a high temperature, if the room was already messed up, then our increase in entropy won't be so large. Okay, let's try a calculation using that equation. Pause the video, try the question, come back for the answer. So we're trying to calculate that change in entropy. It's supposed to equal the heat added divided by the temperature. Temperature's got to be in Kelvin. Let's calculate the heat added from thermodynamics. We know that that will equal the mass times the specific heat capacity times the change in temperature. Make sure you're using MKS units. The mass would be 0.3 kilograms. Specific heat capacity of water, 4,200 joules per kilogram degrees Celsius. And our change in temperature, remember, change in temperature is the same in Celsius or Kelvin, so that's going to be 10, let's say, degrees Celsius. Multiply that out, and you should get 12,600 joules. Our temperature, well, our temperature is actually changing, so we'd like to use a typical value or an average value for the temperature, and that would be 25 degrees Celsius, halfway between 20 and 30. But don't forget, you've got to convert that to Kelvin to use this formula. So 25 plus 273 will give 298 Kelvin. And that means our change in entropy is going to be 12,600 joules divided by 298 Kelvin, which will give you an answer of 42.3 joules per Kelvin. So let's summarize the big ideas from the video. The first one would be, what is entropy? Well, it's a measure of disorder. And it's fairly easy to recognize when you've got higher or lower entropy. You're going to have less entropy when things are colder. When things are separated or organized. We then talked about the second law of thermodynamics being expressed in terms of entropy. And that was simply to say that the change in entropy for a closed system or for the universe as a whole is always going to be greater than or equal to 0. If a process has no change in entropy, it's going to be reversible. And at least for right now, that just means we could take a film of it, run it in reverse, and it would look perfectly normal. And then we saw how we could calculate entropy changes. when heat is given to a substance. And it'll just equal the heat that's added to that substance divided by the temperature of that substance in Kelvin. And that's all for today, folks. Thank you very much.